Hello, this is Phil.
Hello, this is Emily.
Welcome to the Deep Dive. Today we're taking a deep dive into PCA.
Or Principal Component Analysis.
Yeah, that's right. We've got these notes here from Professor Wu and,
Lots of linear algebra.
oh yeah.
Some serious matrix magic going on.
Yeah, but don't worry, we'll break it all down for you.
So think of PCA as a way to simplify complex data. If you have a giant cloud of data points and it's scattered across multiple dimensions, PCA helps us find the most informative shadow of that cloud,
Shadow.
projecting it onto a line that captures the most important variations.
Interesting. So our notes start with this thing called centering the data.
Yeah.
Which sounds pretty basic.
Right? It sounds pretty basic, but it's actually super important.
Okay.
It's like setting the stage for PCA.
Right.
It's all about shifting our perspective so that the average of our data becomes our new 0 point. If you can imagine you have these data points and they're just scattered around and you move them so that their center of mass is right at the origin of your coordinate system.
Oh, so it's like creating a new reference point.
Exactly.
A new center of gravity for our data.
Exactly. And this seemingly simple step has some pretty profound implications for how we analyze the data.
Okay.
It sets us up to find the directions of maximum variance around this average point, and that's really the heart of PCA.
Okay, so it's like we're recalibrating our instruments,
Yeah.
to focus on deviations from the average rather than just absolute values.
Exactly.
Okay.
Now, when we talk about finding directions of maximum variance, it might sound a little abstract,
Right.
but there's a really intuitive way to think about it.
Okay, lay it on me. I'm all ears.
Think about it this way. Variance implies information.
Okay.
So if our data points are all spread out,
Uh-huh.
it means there's a lot of variation, a lot of information to capture.
Right.
But if they're all clumped together, there's less variation and less information to work with.
So the more spread out our data is after we project it, the more of the original information we've managed to preserve.
Exactly. PCA aims to find the line that after we project our data onto it results in the maximum variance.
Okay.
And by doing so, we're finding the line that captures the most, essence of that original data cloud.
Okay, so I think I'm starting to see the big picture here.
Yeah,
We're centering the data
right.
to establish a new reference point, and then we're looking for the line that maximizes the spread of the data when projected onto that line.
You got it.
That's the core idea, right?
That's the core idea.
But how do we actually find that line?
Right. That seems like the tricky part.
Yeah, that seems like the tricky part.
That's where the magic of linear algebra comes in.
Ah, the linear algebra.
Specifically, we use eigenvectors and eigenvalues.
Oh, yeah. Professor Wu definitely mentioned those.
Yeah.
I remember something about eigenvectors pointing us in the direction of maximum variance,
Mm-hmm.
and eigenvalues telling us how much variance is captured in that direction.
Exactly. It's like eigenvectors are these special directions within our data space, and eigenvalues are their corresponding strength or importance scores.
Okay, so we need to find the eigenvector with the highest eigenvalue.
Right.
That would be the direction that captures the most variance, the most information about our original data.
You got it.
Okay, this is starting to click now.
Yeah.
We're centering the data and then finding the eigenvector with the highest eigenvalue. And that gives us the line that maximizes the variance of the projected data PCA in a nutshell.
You got it.
Okay.
Now, there are a couple of important details we need to unpack to fully understand how this all works.
Okay. All right. So what's next on our PCA adventure?
Well, before we jump into the nitty-gritty of calculating eigenvectors and eigenvalues,
Okay.
we need to talk about how we represent our data and its variance in a way that makes it easier to work with mathematically.
Okay. So we need to set up the problem in a way that our linear algebra tools can handle.
Exactly. And that involves representing our data as vectors and matrices. Might sound intimidating, but trust me, it's going to make everything much clearer and more elegant.
All right. I am ready to embrace the elegance of matrices. Let's do this.
Okay, here we go. So let's start by revisiting the idea of variance
Okay.
and how we can express it using vectors and matrices. Remember, we're interested in the variance after we project the data onto a line.
Right, because that projected variance tells us how much information we've preserved after reducing the dimensionality.
Exactly. So let's imagine we have this line
Okay.
that we want to project our data onto.
Okay.
Each data point, after being projected, will have a new coordinate on this line,
Okay.
which we'll call alpha.
Alpha. Okay.
And we want to find the line that maximizes the variance of all those alpha values.
Okay.
But remember, we're not dealing with individual data points anymore. We're working with vectors and matrices.
Right. So how do we express the variance of those alpha values in a way that incorporates vectors and matrices.
That's where the concept of the covariance matrix comes in.
Okay, I remember the covariance matrix.
Yeah, it's a powerful tool.
But I'm a little fuzzy on the details. Can you refresh my memory?
Absolutely. So imagine you have data with multiple features like height and weight.
Mm-hmm.
The covariance matrix tells us how these features are related.
Okay.
So, for example, it can tell us if taller people tend to be heavier, or if there's no clear relationship between the two.
So it's like a measure of how much two features covary.
Exactly.
Or change together.
Exactly. And when we're dealing with PCA, the covariance matrix is really important.
Okay.
Because it helps us find the eigenvectors and eigenvalues that we
Right.
need to maximize the variance of our projected data.
This is all starting to come together now.
Yeah.
We're using the covariance matrix to find those special eigenvectors and eigenvalues that point us in the direction of maximum variance.
Exactly.
Okay. I'm excited to see how this plays out.
Well, get ready because this is where the real magic happens.
All right.
By analyzing the eigenvectors and eigenvalues of the covariance matrix, we unlock the secrets to maximizing variance and finding the most informative shadow of our data.
Okay, I'm officially hooked. Let's unravel these secrets and see how we could put this linear algebra wizardry into action.
Let's do it. So we've got our data all set up, represented as vectors and matrices, and
Right.
we've got this covariance matrix
Right.
that captures those relationships between our features.
Mm-hmm.
Now, the key of PCA is understanding that the eigenvectors of this covariance matrix, they give us these special directions
Okay.
along which our data varies the most.
So the eigenvectors are like signposts,
Yeah,
pointing us towards the directions of maximum variance.
exactly.
Okay, I like
And
it.
each eigenvector has this corresponding eigenvalue
Right.
that tells us just how much variance is captured in that direction.
So it's like a strength rating.
Yeah, like a strength rating for each direction.
Okay, so if we can find the eigenvector with the largest eigenvalue,
Yeah.
then we found the direction that captures the most variance, the most information.
You got it.
Right.
And that eigenvector that becomes our projection vector, it's the direction onto which we project our data to create that shadow
Right.
that preserves as much of the original information as possible.
Okay, so this is where it all comes together.
Yeah.
We're using the eigenvectors and eigenvalues of the covariance matrix to find the best possible projection,
Right.
the one that maximizes the variance of that projected data.
Now, finding those eigenvectors and eigenvalues might seem a bit daunting,
Yeah, a little bit.
but conceptually, it's all about solving a specific type of equation.
Okay.
Remember those eigenvalue equations Professor Woon mentioned?
Vaguely, yeah,
Yeah.
something about finding vectors
Yeah.
that, when multiplied by a matrix,
Yeah.
just scale by a constant factor,
Right.
and that constant factor being the eigenvalue.
That's it.
Okay.
And in our case, the matrix we're dealing with is the covariance matrix. So solving that eigenvalue equation for the covariance matrix gives us the eigenvectors and eigenvalues we need for PCA.
All right, so we've got the math figured out,
Yeah.
but how do we actually choose which eigenvector to use? I mean, there could be multiple eigenvectors.
You're right. There can be multiple eigenvectors, each corresponding to a different direction of variance.
Wow.
But here's the beauty of PCA.
Okay.
We simply pick the eigenvector with the largest eigenvalue.
So it's a ranking system.
Yeah, it's like a ranking system.
Yeah.
We choose the variance champion,
Okay.
the direction that captures the most spread in our projected data.
Gotcha. And what if we want to reduce our data to, say, 2 dimensions
Yeah.
instead of just 1?
We simply pick the top 2 eigenvectors
Right.
with the largest eigenvalues.
Wow.
So we're essentially choosing the 2 directions that together retain the most information about the original data.
This is amazing. We're using linear algebra to distill the essence of our data,
Yeah.
to find those hidden dimensions that capture the most variation.
And what's even cooler is we can actually visualize this whole process.
Oh.
Imagine plotting our data in its original high-dimensional space.
Uh-huh.
The eigenvectors of the covariance matrix are like these axes, these lines,
Okay.
that point in the directions of maximum spread.
So it's like we're finding the natural axes of our data, the ones that align with the directions of greatest variation.
Exactly. And by projecting our data onto these axes, we're creating a lower dimensional representation
Right.
that preserves as much of that original structure as possible.
Go.
We're essentially rotating our data
Right.
to align it with these natural axes of variation.
This is blowing my mind. We're not just like randomly choosing dimensions to project onto me.
Right.
We're finding those special directions that are inherent to the data itself.
Yeah, it's like uncovering the hidden geometry of the data.
Exactly.
That's a fantastic way to put it.
Yeah.
PCA is all about finding those hidden geometric patterns, those directions that reveal the most important variations in our data.
Okay, I'm officially a PCA convert. But there's one thing I'm still curious about.
Yeah,
How do we know how many dimensions to reduce our data to?
that's a great question.
I mean, we could go all the way down to one dimension, but we'd probably lose a lot of information.
You're absolutely right. Choosing the right number of dimensions is crucial.
Right.
Reduce too much and you lose important information. Reduce too little and you haven't really simplified your data enough.
So how do we strike that balance? How do we find the sweet spot?
Well, there are a few different techniques. Okay. But one common approach is to look at the eigenvalues themselves.
Okay.
They actually provide us with some pretty valuable insights into how many dimensions are truly important.
So eigenvalues can guide us in choosing the right level of dimensionality reduction. Tell me more. I'm all ears.
So remember how each eigenvector has that corresponding eigenvalue? That tells us how much variance it captures?
Right.
Well, if we arrange those eigenvalues from largest to smallest,
Okay.
and we plot them, we often see this really interesting pattern.
Okay, like what kind of pattern?
You often see this like steep drop-off in the plot.
A drop.
At some point, it's like the eigenvalues are saying, hey, these first few eigenvectors are capturing most of the variance, but the rest aren't contributing that much.
So it's like finding the elbow in the graph.
Yeah, exactly.
That drop-off point's telling us maybe we don't need all those dimensions after all.
Exactly. It's like a visual cue
Okay.
that helps us decide how many dimensions to keep.
Gotcha.
We can choose to keep the eigenvectors corresponding to the eigenvalues before that drop-off point,
Okay.
knowing that we're capturing most of the important variance.
That's pretty cool.
Yeah, it's a really elegant way to approach dimensionality reduction.
Yeah, we're letting the data itself guide us.
Right.
Using the eigenvalues to tell us how many dimensions are actually meaningful.
And that's the power of PCA.
Yeah.
It's not just about blindly reducing dimensions.
Wow.
It's about finding that most informative representation of our data. Right.
While preserving as much of the original structure as possible.
I think we've covered so much ground today.
We have.
From centering the data to understanding those eigenvectors and eigenvalues.
Right.
And now this clever trick of using the eigenvalues to guide dimensionality reduction, I feel like I've unlocked a whole new level of understanding about PCA.
Me too. It's been awesome exploring the world of PCA with you.
Yeah, this has been great.
Hopefully you now see how PCA leverages the power of linear algebra
Yeah,
to simplify that complex data while retaining its essence.
absolutely. It's amazing how something as seemingly simple as like finding the direction of maximum variance can lead to such profound insights about our data.
Well said. It's a testament to the beauty and power of mathematics
Yeah,
and how it can help us unravel the hidden patterns and structures that shape our world.
couldn't have said it better myself.